Here we have a problem on the Archimedes principle, and I have translated it from Italian. It was taken from an Italian exam, and let's read the problem and then solve it. It's not too long to solve. A hemisphere whose radius is a capital R is floating and partially emerging out of a water container. When a mass m is placed on the surface of the hemisphere, the latter descends into the water by an amount which is 10% of its initial volume. What is the density of the material which constitutes the sphere? Well, we have actually two equations that we can write down. The first one is before we place the mass m onto the hemisphere. So at first we only have two forces. One force is the force which is due to the weight. So it's simply the density of the sphere multiplied by the volume, which is 2/3 pi r cubed. This is the volume of the hemisphere. And then we have G. This is a force due to the gravitational pull, right? And then we have a force which is thwarting this one, which is opposing this one, and it is simply given by the density of the water, rho A. A stands for acqua in Italian, so I will use the Italian notation, but it is just notation. So this is the density of the water multiplied by the initial volume, which I will call V0, and this is not given. And then we multiply this by G. So the initial equation is rho A V0G equal to rho sphere 2/3 pi r cubed times G. Then after we place the mass m onto the hemisphere is going to increase the volume which is immersed in the water by 10%. So we know that this force here will increase by 10%. So we will have rho A V0 times 1 plus alpha, where alpha is simply equal to 0.1 in this problem. So this is the percentage that the volume increases. V0 times 1 plus alpha times G. And here on the right, we still have the same force. We have rho S 2/3 pi r cubed G. And then we have another force, which is simply given by the mass m that we placed onto the hemisphere, and it is something given, times G, right? So from these two equations, we can obtain something meaningful, because from the two, we get that rho A V0 alpha G is equal to mg. If you subtract from this one here, term by term, so you get this, and from this you get V0 equal to mg divided by rho A alpha G. So this is equal to m divided by rho A alpha. And now you can find the density of the sphere from the first one. So the density of the sphere is given by rho A V0 times G, but we have V0 from here, so we have m over alpha times G divided by, of course, we have to divide by this. So we have 2/3 pi r cubed G, and you can rewrite this as m divided by, so you can simplify G, and you have 3 here, 2 pi r cubed alpha. And this is the final formula to solve the problem.